What's going on YouTube? This is going to be a lengthy 4-part series attempting to explain the methods that were used to repair, overhaul, and modify this 1974 Fender Twin Reverb tube amplifier. In part 1, I will address the customer's initial concerns and explain my repair decisions as I go along. We will also be doing a complete overhaul on the electrolytic capacitors throughout the amp. Now, with that being said, many other repairs and modifications will take place in parts 2 through 4 that may be of interest as well. It is worth noting that I am not a professional technician and that I am self-taught. This video was made primarily to further embed the fundamentals that I've attempted to learn over the past few years. If I find an error, I will do my best to make a note in the description. Lastly, this video series is best suited for someone who is just beginning their journey into the world of tube amplifiers and would like a basic understanding of how tubes work, what bias is, and how to address several repairs, and how to dabble a little bit into modification. If this sounds like it would be of interest to you, please stick around and we'll get started. When I initially received this amplifier, the customer's main complaint was that the power tubes were red plating and getting too hot. Usually that is a problem in the bias circuit, so I think that's where we'll begin looking for failures. As we'll find out later in this video series, there's much more wrong with this amplifier, and we'll go through and attempt to address each one of these issues. So in order to understand what bias is and how it actually works in the tube, I'd like to try to explain first how a tube actually works. This is just a diagram of the elements that actually makes up just a very basic tube. So from bottom to top, we've got a heater, a cathode, a control grid, and a plate. Each one of these elements has a specific function and task, and we'll go through that. So when you turn on your amp and you look in the back, you see that the tubes are glowing. What's responsible for that is a heater. The role that this plays is to actually heat up what's called a cathode. Once that cathode gets hot enough, it starts to throw off electrons, negatively charged electrons, and we're actually throwing in positive direct current onto the plate. So we've got negatively charged electrons and a positive plate. Those electrons are going to want to go towards that plate and then out of the wire that's connected to it. Now, a tube's primary purpose is to amplify a signal, and this is how they do that. So we've got a control grid that's actually connected to our guitar. It goes into the tube, and think of it like almost like a screen door in between the cathode and plate. So again, we have negatively charged electrons coming off of the cathode wanting to go to the plate. Let's say that there was no control grid. There's nothing to impede their flow. When you strum a chord or play a note on the guitar, those pickups that are in the guitar actually create a small amount of voltage, and all that is alternating current. So it's the voltage is going positive, then negative, positive, then negative. Since that's connected to the control grid, when let's say your guitar signal comes in and it's in its positive state, it will charge that screen door more positive, and so that allows the flow of electrons from the cathode to the plate. Now when your guitar signal comes in its negative state, it will negatively charge that control grid. When that happens, these negatively charged electrons are repelled from the control grid, impeding the flow from the cathode to the plate. Now the flow of electrons from the cathode to the plate is extremely high in comparison to the signal strength of your guitar. So again, we're controlling a much higher current with a very low signal, and at that point we have our amplification. Now when it comes to biasing, the purpose for that is to kind of set a speed limit for how much electrons or current can pass through this tube at idle, which is when no chords are being strummed and no notes are being played on the guitar. If there's no biasing present in this tube, we've given a no speed limit environment to these electrons, so they're just going to go, and then this tube is going to start to get red hot and it will fail. So we need to set a speed limit. There's a couple ways that we can achieve this. One is through what's called cathode biasing, and the other way that we can bias the tube is through the control grid. We can start with cathode biasing. The way this is achieved is that the cathode is connected via resistor to ground. What that will do is impede the current flow through the tube. And we can actually vary that amount to allow more current to flow through the tube, or less current to flow through the tube, depending on what value that resistor is. Now the Fender Twin is actually grid biased, so what we'll do is we'll apply a negative voltage to this grid. Let's say in this instance, I think the schematic calls for negative 53 volts on this grid. And so with the control grid being negatively charged, it's always going to be in somewhat of a suppressed state of allowing that a flow of electrons to pass from the cathode to plate, setting that overall speed limit. Again, if this wasn't negatively charged, we've got free reign for these electrons to pass as fast as they want to, and overheating the tube. So to begin our repair, what I'm going to do is actually check this control grid on the amp to see if there's any negative voltage present. Alright guys, I've got the 1974 Fender Twin Reverb on the bench currently. We're having an issue with V9 red plating getting way too hot. We're going to start by checking the negative voltage coming off the bias circuit. So what we're doing is we're coming off this bias capacitor. We're going to follow this down to the fluke. We're going to be monitoring negative voltage. We're also going to be monitoring our plate current throughout the amp with this mass stack. This string of diodes here is what kind of helps rectify the alternating current coming in from the transformer, and then it hits the filter capacitors in the back. So if you've never worked on tube amps, these things are lethal. They will kill you if you don't know what you're doing. So what I've done to make this amp safe to work on is, long story short, when you turn on the tube amp, you'll put maybe 500 volts direct current onto the plates of the tubes. That current, or that charge, is held within very big filter capacitors. It's actually not on this side, it's in the back, and they'll continue to hold their charge even after the amplifier is turned off. So this is a method to safely discharge those capacitors. What I've done is come off these string of diodes, and this actually goes to a discharge stick that I homemade. It's just a resistor that goes to ground here, and so what happens when I turn this amplifier off is that the remaining charge on those filter capacitors will come surging down this wire and hit the chassis, and then be safely dumped to ground. And I can monitor how much of that plate current that's still held within those filter capacitors coming off pin 1 of V1 here. Since I have this set up the way I do, it is actually simulating a short to chassis. So I'm actually putting,
500 volts onto the chassis of this amplifier. Now that will get dumped to ground, and I've kind of built a homemade current limiter here. So if you don't have this current limiter and you do the same procedure, you'll most likely blow a circuit in your home. There's just a rush of electricity hitting your circuit breaker there. It'll probably flip. But I will be using a variac, which only permits as much voltage as I want to go to the amplifier. So I'm going to slowly ramp this up, because all we're looking for is negative voltage from here. And I don't need much current going through this amp to see if this capacitor in this circuit is giving me negative voltage. I come over to my variac, it is down. Let's slowly ramp it up. Let's put 25 volts into the amplifier. We look at our plate voltage here. We've got about 22 volts. Now most of that voltage is getting thrown to ground. We can actually see the current limiter being engaged. The more voltage that I throw at this amp, this current limiter is impeding that flow, and it's being dissipated as heat and light. So that's at only 25 volts. So if I throw 120 at it, let's turn it up a little bit. Let's get it to focus. Let's go to 50. You can see how much brighter the bulb got. So if I throw 120 at that, imagine what that would do to your circuit breaker. Anyway, we're only up to 30 volts on our plate because most of this signal is going to ground. If I unhooked this, we might have 200 volts present in here, but I'm getting rid of all that voltage to ground. Anyway, we look at our negative voltage. We have no negative voltage. So right now, these tubes are free to get as hot as they want, and so there's definite red plating throughout. So one more thing, if you are working on your tube amp and you got the chassis out, this transformer, or the output transformer, will expect to see a load on it, a speaker load on it. And if you're doing any oscilloscope work where you're injecting a signal and you don't want to hear it at full blast, what we'll do is we'll kind of emulate resistance of a speaker. And so what I've got here is a what's called a dummy load. It actually comes through and it's this mess of cables, but it ends here. And this is just simply an 8 ohm, I forget how many watts, I think it's a 100 watt resistor, an 8 ohm 100 watt resistor. So it simulates a speaker, or the load of the speaker, so that the transformer actually sees a load there. Think of it like putting a car in neutral and flooring it. Pretty soon that engine's going to burn up, but if you put it in gear and floor it, it sees a load, and then the engine's happy. If you're working on your tube amp, never turn it on unless you've either got a dummy load hooked to the output or a speaker hooked to the output. Also, it's worth mentioning that with this method of discharging the capacitors through a discharge stick to ground, you need to have that ground pin working correctly, being plugged into the outlet. When I received this amplifier, this is what I was given, and I plugged it in and was monitoring my plate voltage. And let's simulate what would happen. So this simulates the amplifier being plugged in with its original cord plugged into the amp, and so I've got the hot and neutral, but I've got no escape to ground, which is what I've hooked everything up to. That's my safety. If I come in here and I touch, especially that area right there at the end of that string of diodes, that I'm gonna get hit with 400 volts. That's a bad day. So what I actually had to do, you can probably see my tape job. I had to cut an extension cord and wire up a working ground connection. And I've since ordered the new plug that should be within spec. But let's do this test again, and let's look at the plate current and the charge on the filter capacitors. So everything's hooked up the same way, except I've removed the discharge stick from my high tension. Let's go back to the variac. Variac is off and is down. I'll turn it on. Let's just throw. Let's throw again about 25 volts onto this amplifier, and let's look at our plate current. We've got 105 volts direct current at only 25 watts being fed this. The normal wall outlet, obviously is 120. We can even go, let's go to 50 volts. You can see now that the current limiter is not being engaged. At 50 volts, I've got 182 volts on the plate and in those filter capacitors. Now watch what happens when I turn the amp off. So I turn it off. So you're thinking the amp is off, and you go start touching things in that amp, you're gonna get bit by 150 volts. But that was only at 50 volts being fed to the amp. It would be probably double that if you had plugged that in. You can see how slow it's discharging. It's taking forever. Now when I have that discharge stick hooked to the high tension, it quickly dissipates this. So right now the amp is off, but it's still holding that charge. Just be careful if you're working on this sort of stuff, and have a safe way to discharge the capacitors. All right, I've got the new bias capacitor installed. Everything's hooked up the same way. Again, we're looking for negative voltage and monitoring our plate current. Let's throw around 25-30 volts on it. Plate current is 22, and we now have negative voltage. So this is looking good. All right, the new bias capacitor is installed. I've also reinstalled the tubes, and we're going to check to see if they're red plating. Okay, looking pretty decent. Little static. Alright, so it seems the red plating issue has been finally taken care of. However, when I play the amp, it is extremely quiet. We're actually checking to see if the correct amount of negative voltage is coming off of the bias circuit. We've got a schematic and this is actually a layout, but we're looking for negative 63 volts there on that capacitor that I changed, and so we're monitoring that here, and we're actually also monitoring the plate voltage as well. So right now we got 227 volts on the plates of V1. We're going to see how much negative voltage is actually coming off of this capacitor. Look down here, negative 60 volts. We compare that to Fender's schematic, negative 63, so we are within a good margin there. So we're going to have to do some more investigating to see actually why this is so quiet. I haven't replaced this other white capacitor up there, so we will check the voltages on that as well. Alright, we are checking the negative voltage of this other bias capacitor. We're at negative 50, around negative 53. We compare that right here, negative 52. So we're in spec with that one as well. Let's see what else could be going on with this thing. Alright, so after some experimentation, I believe I fixed the red plating issue. However, when I play through the amp, it's extremely quiet, and so I started suspecting these power tubes might be fried. After doing a couple tube swaps, I kind of got the same result. So that brought me to this cabinet. This should be a 4 ohm load, 2 8 ohm speakers, and this guy's actually loaded with a 115 at 8 ohms, and so that's something that you can safely do as far as mismatching those impedances. So I brought in another cab with a single 12 8 ohm speaker, a noticeable increase in volume. I know sometimes if you go to 16 ohms, it'll kind of reduce the volume, but since they were both 8 ohms, I didn't suspect it. So while under test, I was pleased, I was relieved as I was playing. I got a noticeable increase in volume. I noticed a malfunction here on the 6L6s, these old RCAs. I actually pulled these out of an old Basement 10 that's been giving me issues. I don't have any extra in working condition 6L6s. Unfortunately, I should get some. So I got these guys giving me some fits, and so that actually might be in part what's wrong with the Basement 10. So we're going to swap out some other power tubes for these guys and repeat that test to see if we can't get this guy to stabilize once again. All right, so we're back to the original tubes on the left side. All right, so we got those tubes swapped out. It seems to be a tube failure in the old RCAs and the Basement 10. The original tubes with it seem to be working. So we're going to do a sound test. I've got the amp running to the Mojo Tone cab with a Fender 8 ohm 12 inch speaker in it, and not the 8 ohm 15 inch speaker. So we're maybe 70% of the way up. We kind of got it cranked a little bit, but it doesn't sound bad. There's no reverb. The reverb tank is not hooked up yet, so this is just a dry signal. But it's got some good chimey, Stevie kind of sounds to it. Yeah. So I think this thing's got great potential. I'm very anxious to hear what it sounds like with the reverb tank hooked up. So yeah. All right, so after having some fun, kind of playing around, we're gonna get back at it. So far, I'm happy with the volume increase we got from switching from the 15-inch speaker to the 12-inch speaker at 8 ohms. We're actually in the normal channel right now. I've actually got the vibrato tube pulled. Yeah, I've got the vibrato tube pulled, and then I've got the reverb tubes pulled as well. So since we're not testing the vibrato circuit at this moment, I used a couple of these tubes to kind of swap around to see if there was any bad ones kind of present. So the next step is to go through and check the vibrato channel. If that's working correctly, we will move on to checking the actual vibrato circuit or effect to see if that's working properly, and then we will move to the reverb and kind of go from there. Just plugged into the second channel, the vibrato channel, to test, see how that's coming through. Here's a little sound test. It sounded pretty good to me. I've also, I don't know if you can see this. Here's the reverb tank. I got that going to the inputs and outputs here. So let's get some of this reverb going. Let's see if that is actually working. 1, 2, 3, 4. And it looks like we've got reverb. Look at that. Sounding good. We're going to now test the reverb circuit. I've got both the intensity and speed up about halfway, and I do have the foot switch available here to check this as well. So we'll check how if the foot switch is controlling the reverb properly. Right now it is off. I'll hit the reverb. Looks like that's working. Vibrato. Sounding good. Happy with that. Working vibrato and reverb. Like I said earlier, when I received the amp, this was kind of how the plug was presented to me. You can see it's missing a ground, and so this is where the plug comes into the amp. We're going to unsolder all that and get a new cord going. I've got a new guy right here. We'll cut to length and solder it in. So after further examination of this power cord and how it's hooked up, it looks like it follows through to the convenience outlet here. I've never once in my life used this this feature, so I'm thinking I'm gonna bypass that. Coming over here to the ground switch, once again, I've never had to use it, and then we get, I don't know if you can see that blue capacitor back there. Believe that's the infamous death capacitor, the 0.7 microfarad. I think it's 600 volts. I haven't, it's the sole purpose for it being there is to eliminate hum. I haven't checked to see the difference in the hum, but I'm thinking I'm probably going to bypass that whole thing and the hum and actually come straight over to the fuse here. Just got the ground lead unsoldered from chassis. Usually when leads are soldered directly to the chassis, you got to get kind of the big guys out to take care of producing enough heat to get that solder to melt. Anyway, so I've got a mess here. I'm going to try to clean up and tidy. Just got the new lug ready to accept the ground wire from the new power cord. And then we need to start disconnecting the existing leads from the original power cord. Again, we're going to bypass the service outlet and the ground switch and wire it directly into the fuse and the transformer. Now got the power cord out. Got the other leads disconnected, and so we'll attach our hot lead onto the fuse and our common to the transformer. We'll have to splice that into the that transformer lead, the white one there. Two of the three connection points are going to be real easy to solder in. There's one. The other one here is on the end of the fuse, but this guy goes straight into the transformer. So we're going to have to splice these wires together. I'm going to use what's called a married technique. So I'll show you what that looks like here in a sec. We now have our spliced wires here. We're going to throw some solder on them and some shrink wrap, and we'll move on to the next connection. Finally have the new power cord installed. Ground. We got it tapped into the transformer, and then it is going to the fuse. Since we've bypassed both this guy and the hum switch, I'm going to remove this hum switch here and make it a little bit easier to get to that capacitor that we're not using anymore. And so what I think I'm going to do moving forward is kind of a complete overhaul of this thing. We will replace the other bias capacitor as well. We're going to go ahead and replace all the other electrolytic capacitors in here. It's the white ones in there. And then there's a couple, these gray ones down here we'll do. We'll get those changed out, and then we're also going to do the filter capacitors as well, as I think those are original. It's a shame because the amp is dead quiet. It sounds good, but the life of these capacitors, especially filter capacitors, from what I've read, is around 10 years. And this being a 74, they've done their job quite well. But we're going to replace them with I think these are F&Ts, and it's kind of like the equivalent of changing the oil, I believe, in a car. And so yeah, we'll pick up from there. Alright, it's been a couple days since I've last worked on the amp. So usually before I even touch anything anywhere, I'll grab a multimeter, I'll throw a lead to ground, and then I'll make sure the standby switch is engaged. Actually come over here to pin 1 of V1, make contact, and there's less than half, I mean, not even that, just a minimal amount of voltage still left in the amp, and I can come over to the high tension as well, and just always just checking a couple spots. I may even even double check. I can use my discharge stick, and even though I've got readings on the multimeter that show safe, I always doubt myself, and so I always kind of assume that I'm doing something wrong, and so I always try to triple check this capacitor discharge procedure over and over. I do not want to get zapped. Okay. Just got out the second bias capacitor, the 80 microfarad, 75 volt. We replaced it with a F&T 100 microfarad, 100 volt new capacitor. So that should be a good, healthy bias supply circuit now. I also figured this would be good to share. Typically when you get replacement parts in for amps or electronics, typically they're all bent up with a resistor, capacitor, or whatever. And usually we try to be as neat as possible. And if you get one of these smooth jaw pliers, the longer the jaw, the better. This one's actually kind of hard to work with, but you see there's no grooves in these. These are kind of flat. But if you do a kind of a compression squeeze down the length of that lead, you can get them pretty straight, and then when you install them, you can put them in at 90-degree angles. It just makes it look a lot cleaner. Just got the new capacitors installed. We got 1, 2, you really can't see the second one, 3, 4, 5, and 6. So the next step is to kind of fire this guy back up again and see if she's still doing all right. It's been a few days since I've worked on the amp, since I replaced those electrolytics. All I've done at this point is reinstall the tubes, and I've checked both channels just to make sure that I've still got signal through the amp, just to make sure I didn't really botch anything up. So far channel 1 and channel 2 seem to be working well. I think at one point down the road I'll have to end up checking the vibrato and the reverb once everything's kind of hooked back up, but I think at this point I am just going to move forward and move on to replacing the filter caps. So before I start getting to the filter capacitors, I've got a positive lead hooked to the high tension and the negative to the chassis here. I'm just checking to see the remaining charge on my filter capacitors. As you can see, they're pretty much drained at this point. So anyways, we're still gonna go over here to pin 1. I'm gonna flip that standby. Use our discharge stick. And really just make sure that this guy is drained. So I've got the filter capacitors exposed. Looks like 200 microfarad, 350 volt, and 3 20 microfarad, 500 volt capacitors here. At this point, this is the stuff that you don't want to touch unless you're 100% certain that they're discharged. I do have my discharge stick hooked to chassis. I'm going to kind of go through these. Like I said, I've already bled everything off when the amp was flipped around the other way. I'm just going through and just discharging again and again, just to make sure. You can never do this too much. I'll even go as far as to take a volt reading across it as well, just to make sure before before I touch anything. So sometimes when these go bad, you'll start to see them bubble. And I'm looking through here. I think I might see a couple spots that look concerning. But usually though, that electrolytic will start to leak, and you'll start to get hum in the amp. Just any signs of bulging is usually a pretty good indicator that they've gone bad. I'm not seeing anything really too obvious that these are bad, but again, the shelf life of these guys are, from what I understand, is about 10 years, so we're going to go ahead and replace them just as a preventative measure. I got my voltmeter set up. Negative is to the chassis, and I've got my voltmeter on the positive ends of these capacitors. I'm getting no voltage reading as I go through these guys. So at this point, I've discharged the capacitors 2 or 3 different ways, and have confirmed that they do not have any voltage still present with them with the voltmeter. So at this point, I believe they are safe to touch. Here's the schematic for the twin reverb. We've got some of the filter capacitors down here, the 100 microfarad, and then we've got one guy up here, 20 microfarad. So when you do a filter capacitor change, you want to be sure that the polarity is exactly the same. If you're lucky enough to have access to a layout as opposed to a schematic, just kind of shows you how everything's laid out. I was fortunate enough to find one online, in which case it shows me the orientation here. So if you flip one of these into the opposite polarity position, it will explode. So don't do that. So I would recommend not taking all the filter capacitors off at once. I would replace one at a time. The size of these is considerably bigger than the old ones. Because of that, it is recommended to use some silicon-based glue underneath these big guys. You can see even the size difference between the smaller capacitors. So I'm going to throw a little bit of glue underneath them to keep vibration from kind of creating any problems. While I'm in here, I'm also going to change out some dropping resistors. I took this 10,000 ohm resistor out of right here. There's a guy here, there's a guy in between these, and in between those as well. We will replace them with some new ones, just to ensure that they're within spec. This is the type of glue I'll be using to secure the filter capacitors to the eyelet boards. I just got a small strip of it down the side of the capacitor just to help secure it from premature failure due to vibration. Alright, just finished replacing the last filter cap. The next step will be to slowly power up the amp with the Variac to allow these capacitors to form. It's also worth mentioning that if you're doing this yourself, please use a current limiter. If you've got safety glasses, wear them. If not, just stand back from the amp and be sure that you're in a position to where if one of these caps blow or if you see arcing, your hand is near a power switch, preferably not the one on the amp, that you can cut power to it if need be. I'm using a variac to slowly bring up the amp's voltage to allow the filter capacitors a chance to form properly. So right now we're right at about I don't know, I'd say what, 10 volts. So what I'm going to do, I'm just when I'm doing this, I'm just looking for arcing or smoke, and at this point I don't see any, so I think we're good. We've been at 10 volts for a couple minutes, so we will probably turn this up to about 30 and wait a couple more minutes and repeat this process until we're at 120. Alright, so I'm at around 30 volts here. Everything is still looking good, so we're gonna maybe take it up to 40 or 50 and see how she's holding. So we're up to about 85 volts at this point. Everything's still looking good. There's no arcing, smoke. So I'll check back in once we're at 120. Alright, we're at 120 volts in this amp so far. Everything is looking good. I figure the next thing we'll do is actually plug it in and make sure we've got sound and measure some voltages as well. At this point, I think I'm happy with the cap job that was done. I think the amp is stable and the voltages are looking good. I think at this point, I'm going to move on to actually modifying the bias circuit, but I'd like to talk about what biasing is, how it's done, and the various methods that's used amongst the variety of amps that's out there, and then talk about the differences, the positives and negative of each configuration. And then I think at that point it'll be clear why I'm going to do this modification. So I think we're going to end video 1 here. So far we've attempted to explain how tubes work. We've successfully repaired the bias circuit. We've encountered a low volume issue that I will address in a later video. We've replaced the power cord, and we've overhauled the amp by replacing the electrolytic and filter capacitors. In part 2, I will attempt to explain how to measure and modify bias in cathode and grid biased amps. We will also modify the bias circuit in this Silverface to allow the bias to be changed more easily by adding a bias pot. So if you've watched up to this far, I sincerely appreciate it, and I hope to see you in part 2.